Alright, a quick review of substitution. We're going to look at a few problems here in this quick review. General idea with substitution, just remember it's usually best for us to find some quantity that's inside parentheses or under a radical or in the denominator of a fraction, or that meets multiple ones of those characteristics to choose as our substitution. Although that's not always the case, but that seems to be the case, I'd say in my experience, 90 to 95% of the time. So those are the problems we're going to focus on here. Our first problem, the best substitution appears to be u equals 5x plus 4, in which case du is equal to 5 dx, and dx is equal to 1/5 du. So when I make my replacement, this turns into the integral of u to the 5th, and I replace the dx with 1/5 du. I'll bring 1/5 out in front of the integral. And then I could integrate from there. 1/5 times u to the 6th over 6 plus c. So that's u to the 6th over 30 plus c. And then I bring my u back. And you've got the quantity 5x to the 4th raised to the 6th over 30 plus c. And that's really how we generally handle substitution when we have an indefinite integral. In part 2, we have a definite integral, since we have those limits of integration. I'm going to approach this a little bit differently. First, I look for my substitution. The best substitution here appears to be u equals the sine of x. And then du is equal to cosine of x dx. And so this turns into the integral of the square root of u du. Now, at this point in time, we need to talk about what goes on with those limits of integration. I can either leave them off until I bring my u back at the end and then substitute them back in to evaluate the integral. That's probably a more cumbersome method. The better method is to take those limits of integration, convert them over so that they're in terms of u, and replace them so that I don't have to actually bring my expression for x back in at the end when I'm integrating. So the easy way to do that is we're just going to take our substitution that we have, and we're going to substitute those limits of integration into it and figure out what the u values are that correspond to those values of x. So u equals the sine of 0. Sine of 0 is 0. So that limit of integration will be 0 in terms of u. And the upper limit is pi, so u equals sine of pi. Sine of pi is also 0. So wow, in order to evaluate this definite integral, I don't even need to take the antiderivative here. This is the integral from 0 to 0 of something, and so the value of this is just going to be 0. That's another one of the benefits of changing the limits of integration over to be in terms of u, is sometimes it works out nicely like that, and we don't even have to bother taking the antiderivative. Alright, let's look at example 3 here. U equals x plus 1, quantity x plus 1 times sine of the quantity x squared plus 2x plus 3 dx. I'm going to substitute what's inside of the sine function. Again, we're back to an indefinite integral here, so I don't need to worry about limits of integration in this one. And then du is equal to 2x plus 2 dx, which we notice is different from what's left here when we make the replacement. I like to think about, well, what multiple of du is equal to all the stuff that's highlighted in green there. And that's 1/2 du is equal to that quantity. So I'm going to replace that whole quantity highlighted in green with a 1/2 du, and this integral turns into 1/2 times the integral of the sine of u du. Now I integrate. It's 1/2 times the opposite of the cosine of u plus c. I've got negative 1/2 cosine of u plus c. And then I bring u back, and we end up there without any wind. Alright, last one. Now looking at this, some people might think, hey, let's try and substitute the whole denominator, but it's going to work out a lot prettier if we just substitute what's inside of the quantity squared here. So I'm going to make that substitution. U equals square root of x plus 1, because then du is equal to 1 over 2 root x dx. And so if I look at everything that's left over here, that's equal to 2 du. So I'm going to replace that with a 2 du. So this turns into 2 integral of 1 over u squared du. Now I'm going to change my limits of integration over. I'm going to take 1 and 4 and substitute them in here for x and figure out what the corresponding y value is for those x values. When I put 1 in, that's the square root of 1 plus 1, that's 2. And when I put 4 in, that's the square root of 4, which is 2 plus 1, so that limit's going to be 3. And now I don't have to bother bringing u back in the end. I can just substitute the limits of integration after I find the antiderivative. The antiderivative of 1 over u squared is negative 1 over u. And so we've got negative 2 over u evaluated from 2 to 3. So we've got negative 2 over 3 minus negative 2 over 2. And that turns into, let's see, negative 2/3 plus 1, which is positive 1/3. Alright, there's your quick review problems.